In a previous video, we introduced the RRK theory with a couple simple numerical examples. We also derived an equation to calculate the probability of one of the vibration modes getting enough energy quanta for the unimolecular reaction to proceed. In this video, we will simplify that equation, but first, let's define a few variables. Let's say we have a reactant molecule. That may undergo a unimolecular reaction. For example, decomposition or isomerization. And then this reactant molecule has S vibration modes. All right, we got our first variable here. And then we're about to distribute NH energy. Will be distributed to the S vibration modes. If these vibration modes all have a different vibrational frequency, our calculation will be a little bit more complicated. So we're going to use this assumption here. All these vibration modes have the same frequency. Nu. This will make the derivation a lot simpler. So our second variable is N. So we're going to have N energy quanta to be distributed to this S vibration modes. Now we're going to say, well, one of these S vibration modes is special. If this special vibration mode gets enough energy, a reaction may occur. So there's a special vibrational mode. With a double dagger or more H nu will result in a reaction. All right, so we have another variable here, N double dagger, N S. All right. Now we defined these three variables. We have S vibration modes, we have N energy quanta, and the special vibration mode of this molecule needs a double dagger energy quanta to have this reaction proceed. Now we're going to distribute the N energy quanta to S vibration modes. So we derived this equation before. It's going to be just N plus S minus 1 factorial over N factorial and S minus 1 factorial. This is the total number of arrangements. All right, so when we give N energy quanta to S vibration modes, we have this equation over here to give you the total number of arrangements. Now, what if we need this special vibration mode to get at least N double dagger energy quanta? And then we'll have to kind of reserve N double dagger energy quanta, right? And then the remaining energy quanta is N minus N double dagger. So that means we're just distribute the remaining N minus N double dagger energy quanta to the S vibrational modes. The equation is this. This is number of arrangements after m double dagger h nu is given to the special vibration mode. All right, and when this special vibration mode gets n double dagger h nu energy or more energy, this reaction will proceed. Right, so we got two numbers here: the total number of arrangements and the number of arrangements that may result in a reaction. So the probability of having a reaction is, well, I'm going to just say this is my equation 1, this is my equation 2. So it's going to be equation 2 over equation 1. That's going to be the probability. All right. So if we look at equation 2, this is on top, right? And n minus n double dagger factorial is on the bottom, right? And then equation 1. So we're going to flip this n factorial and s minus 1 factorial to the top of this fraction, n plus s minus 1 factorial on the bottom. And then we cancel this 2. And then we reorganize this equation just a little bit. Okay, so that we can simplify this equation a bit more easily. So what I will do is I will do this. Okay, I will have this n minus n double dagger plus s minus 1 factorial over n minus n double dagger factorial. Okay, so we have this term, and then divided by a similar term. Divided by a similar term. So over here it's going to be n plus s minus 1 factorial, and on the bottom it's just n factorial. So if you look at the numerator and denominator, they look similar. Over here it's just n minus n double dagger, n minus n double dagger is replaced with n. Now we're going to make some other assumptions. Assuming we have many more energy quanta than the number of vibration modes, which is often the case. So we're going to assume n is much greater than s. Not only that, even n minus n double dagger is much greater than s. So that means we have many more energy quanta than the number of vibration modes. All right. Well, you can just say this as well. I mean, if you want to be a bit more precise with stating the assumption. And then I will actually take the logarithm of the probability. All right, the logarithm of the probability. And then we'll use also the Stirling approximation to estimate the logarithm of the probability. This is pretty simple. It's just ln x factorial is just x times ln x minus x. All right. This can be easily proved. So we'll use the two assumptions. On top, we'll use the Stirling approximation on the bottom to estimate the logarithm of the probability. So since we have an exact equation for probability, why do we need to estimate the logarithm of the probability? Why bother? Well, this is because if you look at this exact equation, it looks fairly complicated. If you look at this, if I somehow use these approximations and assumptions, I can dramatically simplify the equation of this probability of this reaction proceeding with n energy quanta. Okay, again, we're going to focus on the logarithm of the probability. All right, the logarithm of the probability is going to be, it's going to be fairly complicated. It's going to be the logarithm of n minus n double dagger, this factorial, minus this factorial, right? And then minus over here n plus s minus 1 factorial, subtract n factorial. All right? And each logarithm of a factorial can be decomposed into 2 terms. All right, so we're going to have 8 terms. But what I will do is I will look at this x times ln x term first. All right, so it's going to be just n minus n double dagger plus s minus 1 times ln n minus n double dagger plus s minus 1 minus n. There's a reason I do this. Okay, so I'm focusing on this x times ln x first. And notice that I got rid of the factorial sign. Okay? All right, so the first 4 terms. And then we have 4 more terms, but pay attention to the negative sign. So we got 4 more terms. We're going to have n minus n double dagger plus s minus 1 minus n minus n double dagger. All right, pay attention to this negative sign here. And then we're going to need a plus sign, n plus s minus 1. It comes from this factorial here. And then minus n. All right, so now it's complete. Okay, so over here, you can see in this square bracket, we have s minus 1. Within here, we have also s minus 1. Right? So you have minus s minus 1 and plus s minus 1. So these 2 square brackets, they cancel. So now you can see why I did that. All right, so we have 1, 2, 1, 2, 3, 4 terms. We'll further simplify these 4 terms. So remember, I made a assumption. A minus n double dagger is much greater than s minus 1. Of course, if that's the case, n is also much greater than s minus 1, right? So look, I'm going to derive this first. I'm going to derive this a plus delta times the logarithm of a plus delta, okay, minus a times ln a first. Okay, I'll work on this, assuming a is much greater than delta. Okay, delta is really small. So why did I do this? Well, you can say this a is going to be n minus n double dagger here. And this delta is going to be s minus 1 here. So really, if we can derive this, we can simplify the first bracket easily by replacing a with n minus n double dagger. So this is going to be our a, and this is going to be our delta, right? And this is going to be our a, this is going to be our delta, this is going to be our a, this is going to be our a. And then we can also easily evaluate the second square bracket in the same line. And this time, we're going to say n is our a, and minus 1 is our delta. So this is a, this is delta. and then this is A, right? So it's just for simplicity. Okay, how do we derive this? How do we make approximation? We're going to make approximation using this Taylor expansion of logarithm, all right? So it's going to be this. A plus delta is going to be actually A times 1 plus delta over A, right? I mean, this is just simple algebra, right? This is just simple algebra. It's just maybe I need to use a square bracket, a curly bracket now. A plus delta, and then over here we have ln A plus ln 1 plus delta over A ln A, and then we have A plus delta times ln A, right? So this guy times A plus delta, and then A plus delta times, okay, now I will use the Taylor expansion or Maclaurin expansion for this logarithm. It's going to be just delta over A, okay, minus A ln A, all right? So again, if you are curious, I want to tell you this, okay? I want to tell you this. And then you can put a negative sign here. It's going to be fairly accurate, right? So the logarithm of 1 plus minus a very small number is going to be plus minus that very small number. So that's what I did here. And we need to delete this guy because they cancel, and then we get delta times ln A. All right, and then we get A times delta over A. It's just delta, and then plus delta squared over A. We do have 3 terms here. Oh, by the way, it's better to use approximation sign here. We do have 3 terms here, but this term is much smaller than delta. Okay, so this is much smaller than delta. Well, this is quite obvious because delta is delta over A is much smaller than 1 because delta is much smaller than A. That's our assumption here, right? S minus 1 is delta. N minus n double dagger is our A. Okay, n can be our A as well. So what I will do is I will get rid of this. Okay, so if you look at these 3 terms, actually delta ln A is greater than delta. Delta is much greater than delta squared over A. Okay, so now we get a simplified equation. We're going to plug it in to here, to this line, all right? And then we're going to use this equation for this line as well, all right? So we got the simplified probability. It's going to be delta times ln A. Delta is S minus 1 times ln A. A is n minus and double dagger plus delta. All right, this is our first bracket in which A is n minus n double dagger. Now we have our second bracket. Okay, our second bracket is here, but again, I mean, using the same formula, we'll see, well, delta is just S minus 1. Over here, A is n, all right, and then plus S minus 1. Now you see why we're doing this. S minus 1 and S minus 1 cancel, right? And then we'll have very simple equation. Okay, this is very simple. Now I'm going to copy this equation on the next page. The probability of the reaction occurring is, well, the condition of the reaction occurring is that the special vibration mode gets enough energy. For example, n double dagger H nu energy, or more than that. So that's the probability is going to be, ln probability. Is this. So the probability is going to be e to the power of s minus 1 times ln n minus n double dagger on top and on the bottom. And this is simplified to over here, this expression, s minus 1. Okay, let's again look at the physical meaning of S and double dagger and N. S is the number of the vibrational modes. N is number of energy quanta available to all vibrational modes, or to be distributed to the vibrational modes. This is number of energy quanta needed by the special vibrational mode for the reaction to occur. All right, so over here. And also we can rewrite this probability for the reaction to occur by multiplying this in by h nu. All right, so it's going to be nh nu minus n double dagger h nu. All right, so nh nu is just the energy, right? Energy, and on top it's going to be energy minus e double dagger s minus 1. All right. Although conventionally, when we are talking about just a single molecule, people often use epsilon instead of uppercase E, letter E. So, all right, you can do that as well. So epsilon again is the energy to be distributed to S vibrational modes. Okay, we have S vibrational modes of this in this unimolecular reaction, or in this reactant molecule. S epsilon double dagger is the amount of energy again needed by the special vibration mode. When I say special, I mean actually this vibration mode is the vibration mode of interest. When this vibration mode gets enough energy, the desired reaction may occur. For the desired reaction to occur. All right, later when we have a more complicated cases, when we are looking at a molecule with multiple vibrational modes, which given enough energy can result in a different reaction, and then we can compute the branching ratio by using this probability. But for now, let's just say only one vibration mode is special. If this vibration mode gets enough energy, the reaction may occur. So this is a simplified model. So this is the equation over here. I'm going to box it. This is going to be the equation used to compute the probability of reaction based on the RRK theory.